Welcome friends, students, kids maybe. We are discussing what is called as a fundamental theorem of integral calculus. How it's been said, integral of f of x dx from a to b is equal to, let's say the integral of f of x is g of x, then is g of x from a to b, which is g of b minus g of a. So basically what I mean, the number whatever we get by subtracting these two of the values, g of b minus g of a. G is supposed to be what they call as an antiderivative of f of x. Antiderivative, or maybe I should say integration. Numerical value whatever it comes of g of b minus g of a, what it was found that it represents the area below the curve f of x, which comes out to be as a very important result for humans, or maybe I'll say in the mathematical history. This actually, g of b minus g of a is what they call as an area below the curve, below f of x between a, I should say x is equal to a and x is equal to b. What we'll try to prove it means this integral whatever we get, it represents the area function. That's the moral of the story. So means, let's say, suppose if area function are denoted with x, then integral from 0 to x f of t dt, we'll say it is termed as an area function. We'll try to prove this. So basically all I have to prove that integral of f is a, so derivative of a is f. I have to prove dA by dx is f of x. We'll try to prove it. Don't be confused with the variables, whatever are they. They are just the notations. I chose it in a proper way so that there shouldn't be any confusion. So let's try to interpret this particular result. Let's consider a function f of x we plot on a graph. So I may consider something like this. I draw a function. The value x, it's in here. I drop a perpendicular. So area function means what? The value to the left of x, whatever is there. Value of the area to the left of x, whatever is there. That means a of x. So whenever I'll say a of x means area to the left of x. This is the function f of x. Sorry. This what we have is the function, sorry, again extremely sorry. This I'll say is the function f of x. If x is the value on the x-axis, then area to the left of x I'll represent as a of x. Maybe this I'll say is a of x. Well, as in suppose if I had to say a of x plus h, then what I should do it? I'll move a little ahead. Maybe I'll say x plus h is whatever it looks. So area to the left of x plus h I'll denote with a of x plus h. I'll also shade with the red line. We'll say that is called as an area to the left of x plus h. So a of x plus h. Maybe I'll shade as this. Already I posted, somebody has written the proof for this. Maybe I'm following more or less the same path, but I'll just do the improvement at the last stage. According to me, whatever I felt, it's easy. So maybe red shaded portion, whatever is there, I say that is called as an a of x plus h. So now this is the function x. I denoted area function in such a way that if you consider any value of x on x-axis, corresponding value of function is f of x, then to the left of that x, whatever the area is there, I'll call that as an a of x. So let's say, suppose if I'll now consider a of x plus h minus a of x, well, then that comes to be as this particular area within this strip, or I should say within this rectangle, a of x plus h and a of x, if I subtract, means this a of x plus h is red, from that suppose if I subtract black, I might get this strip. Then maybe I'll say strip, I'll horizontal line, I used it for the strip. So this is a of x plus h. No, sorry. This is a of x plus h minus a of x. It says this particular horizontal shaded area, whatever is there. All you have to prove that a dash x is equal to f of x. So if I'll write the definition for a dash x according to the definition of limits, whatever has been given by Sir Isaac Newton, what I'll say that a dash x is equal to limit of, I'll have to prove this in fact, a dash x is equal to f of x. So how I'll move on, first of all let me cancel this. To prove that a dash x is equal to f of x, therefore, let's say therefore on the next line, a dash x will gonna be what? Limit of h tends to 0, a of x plus h minus a of x, the whole divided by h, which comes to be as this stripped rectangle. Well, then what we know that if you consider that particular rectangle, maybe in this particular shape, that looks down, sorry, this is x and that is x plus h, this is x and that is x plus h. I have to find the area of this particular rectangle. So of course the formula comes to be as length into breadth. Actually it looks trapezium more or less. If you approximate this particular curve as a straight line, it looks as a trapezium, but as the limit they said h tends to 0, this particular part, this line, it comes pretty close to this, means it may be somewhere over here. Now suppose if you see the particular strip, it looks more or less like a rectangle. So that will gonna be length, this, the say height, whatever it looks, f of x, length will gonna be f of x, this whatever is visible, this much part will gonna be the length, and h, if I put the limit h tends to 0, this increment in the x will be very much small, so that I'll say is h. So therefore area of this rectangle, whatever is there, will gonna be what? Limit of h tends to 0, f of x into h, whatever the width increment. Since I put it is pretty small, this h now it will be this much itself. I'll write as h. So how it will be? H nicely gets cancelled, and we get, since this in f of x there is no term in h, I'll get simply the answer as f of x itself. So basically I'll get a dash x is equal to f of x. Well, as in that makes the point. Means derivative of the area function is equal to the function, where the area is, I'll say, below that particular function and the x-axis. Well, as in that proves the particular theorem. Example, what we say, maybe f of x we say as x 2x, and we'll find, if I draw the graph, f of x is equal to 2x, and how it will be. Let's consider f of x is equal to 2x will gonna be a straight line with the slope 2. And suppose if you need the area below f of x is equal to 2x, this I'll say is f of x is equal to 2x. Is a particular straight line. This is y-axis and that's x-axis. This is the point 2. So how much if I drop a perpendicular, corresponding value of x is equal to 2. Not good. So that will be x is equal to 4. F of x is equal to 4, not x is equal to 4, sorry. F of x will be 4. Now area below this particular f of x is equal to 4, you may not need that, but let's also just consider over there. Area below this curve, if I'll have to find, x is equal to 2, this will be 4, I mean. So area below this curve will gonna be this, the red line whatever I draw. Of course that will gonna be a right angle triangle. The area of the right angle triangle, so already we know it's half of product of the perpendicular sides. So it will gonna be half of 2 into 4. Height will gonna be 4. This height will be 4. This is 4. So half of base into height, it will be 4. Now if I integrate this, integral of 0 to 2 f of x dx will gonna be what? Zero to 2 2x dx, which is of course 2 comes out, x square by 2. I substitute the limits, 0 to 2, 2 nicely gets cancelled, so it comes to be as 4. So what I mean to say, this whatever we got, integral, I mean, which is x square. X square represents the area function, means it gives the value of area below the curve at the particular point. So y is equal to x square. If you plot a graph, it's the parabola. Y is equal to x square. If you plot a graph, it's the parabola. It'll be let's say upward parabola, maybe it looks as this. I'll try to be little careful maybe. Well, that's how the parabola maybe it looks. Little correction maybe. This is our required parabola. Y is equal to x square. It represents the area function below the line. Let's not deal with this particular part. So all you noticed it is it takes the value as 4. So even the area below the particular line at x is equal to 2 will be given by this x square function. Let's check at the other particular value. Let's say suppose if it is 1. If I put 1, then this perpendicular will gonna be this, whatever I drew it. F of x was what? 2x. So this was 2. 2 into 1. 2 into 1 will gonna be 2. This is 1. So area will be 1. And if I substitute x is equal to 1 in this area function, this ax is the area function whatever we have. After integrating 2x, whatever we get, that is area function. If I substitute x is equal to 1, even that will give the area as 1, which must be the best interpretation of this particular theorem. So what is the moral of the story? I mean, if you have a particular function, you integrate a particular function, then it gives the area function. Area function means area below that particular curve or area below that particular function. Thing looks simple, but this was a major discovery in maths, which maybe which made the entire trip to the moon possible by calculating the areas of some weird shapes, which was not originally possible by using the ordinary rules. Thank you for listening. Forward it as much as possible if you find it is good. Maths is nice. Thank you. Thanks for listening. Thank you very much, my dear friends.